Okay, to pick up where we left off, we managed to transfer our design, which was a geometric unconventional Paveé, into grasshopper. So we got these sections directly through grasshopper, and we were able to play a little bit more with the placing of stones. In this version, they're still represented by spheres, and that's because we have some refinement to do on our definition. First of all, we need to remove the spheres that are too close to the edge. And second of all, we are going to replace the spheres with the stones to better visualize the whole thing.
So we really want to get rid of the points that are very close to the edge. And so we basically need edges. So we have a surface and we have different ways to get the edges. Like, for example, we could use wrap edges. This would be the surface we want to check, and the naked edges, you see, will provide curves that are either planar or non-planar. Now, this could be a way of finding the one curves that we need, because we really want to check these points against this edge and the opposite one on the other side. So as an example, I want to get rid of this point, this point, this point, and this point, and same would happen on the other side. So basically, these are the non-planar curves, the curves, the generic curves here. So a way to do that could be like, let's filter the curves and check for the ones that are non-planar, and Grasshopper has a component that would help us in analyze and check for the planar ones. There is a component that will look for planar curves. Okay, and so this could be a solution, or a different solution could be something that was close to what we did before. Use the isocurves. Now we know that the surface is parameterized in both directions, 0 to 1. So this curve in this direction is going to be at the parameterization equal to 0, and the other ones will be equal to 1. So we could do it that way for as an example. Curve, spline, isocurve. This is what we use already here. We just place as a surface this one, which is being reparameterized. And UV, well, we can use the panel for this. We just bring in a panel. It's quite useful because not only it can store like text or numbers like we did so far, but you can treat your values as by right-clicking as multi-line data. So once it's set this way, it's perfect for what we need to do, because here is just a matter of typing in the numbers that we need, and they are going to be parameters basically. So 0, 0 is going to be one data, and 1, 1 is going to be the other data. So if I click outside, you see it's like just like a list. And if we provide these two parameters, these two set of parameters that are set, you see, we get we're getting the isocurves that are also the edges. Now, we already discussed this before, and we know that the one curves that are going this direction are going to be the U. Just for the sake of consistency, let's double check this. Yes, the green curves are popping up, and this is what we need. It was just a proof. So now it's time to find a mechanism to filter out the points that are close to a given distance, and we want to control that distance.
All right, so now we need to get the distance of the points from the edge curves. So first of all, we're going to use a component called pull point, and we're going to feed our curves to the component, but we only really need one list with both of the curves, so we can flatten the input. And then we can feed the points that we got from the division early on in the definition in the last episode directly to the component. So the reason that this component has a closest tag on it is because we have multiple ways of pulling the points to a certain geometry. So the component only filters out every other way that is not the shortest one. So what we get is the shortest pull possible. Okay, so now that we got the distances, we need to test those distances against the greater than component. And we want the value that we test against to be controlled by a slider. We can input some reasonable values such as like 0.5 as a minimum value and around 3 or something like that as a maximum value. So right now what we get is a pattern that we can use directly thanks to its data structure to call points from our point list. So yeah, we're gonna get a true-false pattern as we got before. We can feed the points and we can see that the points that were too close based on the value that we fed the larger than component actually just disappeared. And this is pretty convenient because we can decide how long a distance we want from the edge to call these points. So this is exactly what we were looking for.
Okay, we can now just use this called list as the base point for the spheres. And so this will just remove the ones that belong to the points that are no longer in the list.
There we go.
Yes, we already see some of the spheres that are disappearing. And so if we now play with this value, we probably get not much here, but if we go crank up the number, you see more spheres will disappear. And so this will give us some pretty good control over the points that we really don't want to include in our list. And I guess that for our object, this would be the best possible choice.
Yes, it looks perfect this way.
Very well. So it's time to just place the diamonds now instead of the spheres. We know how to control the curves and how many points, the distance, and so on. And so it's really time to finalize our definition, and it's time to introduce the diamond. Now, what I do here, I use as a template a 1 milli size diamond. Now, the reason for that is that you will be able to scale that in Grasshopper using a scale factor that will be equal to the true size of the stone. So let's do that. I will use a parameter, which is a brep, to get the diamond and set that rep to the stone. And now using a transform scale component, it's a no-brainer because the center of the stone is 0.0. The center of the scaling is already located at 0, 0, 0. So this is the geometry and the scale factor. You can use maybe a slider for that. I want to show you something. I was double clicking on the canvas because you can really type in the number in a way that Grasshopper will recognize that that is a slider. The syntax is you will define the starting point. For me is 1.0. Now placing 0.0 already tells us how many decimal points that you want. And then you type minor, and then the next number will be have to be consistent with a decimal point. Let's say 5.0. I'm not going to use that big stones, but just for the sake of explanation. And so you see, once you place enter, this will generate a slider. Now, scaling by a factor of 1 is not going to change this at all. But if we want a 1.5 diameter stone, 1.5 millimeter diameter stone, like the ones that we're using, we are briefed to use because they are in the inventory. You see, just scale this, and this will be the size of the stones. I don't think we need to visualize this. So let's remove the preview from this. Oops. Okay. And so now there is still the rhino stone inside here that was confusing me. We can just remove the visualization from that layer, and we have the starting stone. Okay, so this is the stone for which we're controlling the size. And now we have to place the stone on each individual point that we have on the upper surface.
All right, so now we have our stone scaled and all, and we want to place the stone on the surface. For now, what we have are just points that are apparently are on the surface. But what we need actually is certain properties of the surface at those points. So we really can't work with the points we have directly. What we need is to use a component which is called closest point on surface. We feed our points and the component and the surface, of course, and the component is gonna return the closest point on the surface and actually the UV coordinates for those points. And that information will allow us to use the UV coordinates with another component, which is called evaluate surface. And that is going to provide vital information for aligning the stones in the correct way to the surface.
Okay, so it's a bit confusing because there's a lot of generated geometry by Grasshopper, but basically what we're seeing here are all the frames that are located where the UV points are on the surface, and these are going to be really useful to orient the plane, the stone. Now that stone is oriented according to an XY plane, and we want to transform the orientation. And for that reason, we will be using the transform orient command. So this will ask for a geometry to orient. I have to travel a bit down on the opposite side to pick up my scaled stone and go back to where that component is. Okay, so this is the geometry we want to orient. And then we have a starting plane, which is already XY plane, like the one that is fitting the stone. And then we will have a destination, target plane, final plane. And these is going to be more than one, of course, because we have many stones there. And this is going to be F output of evaluate surface. Okay, so we'll let this go. We already see the stone placed. So maybe it's time to remove the visualization, the preview from this component. And there we go. There we have our stones, nicely placed. And now it's just a matter of, playing with the sliders. So you can change all of the sliders that you
Maybe we
have.
want to select the base surface just to provide a little bit more contrast.
Oh yeah, sure. Let's go and make the upper surface visible. Yep, you have it here, and you have all the diamonds. So as a reminder, this I think was the size of the spheres. No spheres anymore. We can just delete this, I think. Okay, we don't need the spheres anymore. We really have the diamonds, which are the one things that we were looking for. So once again, maybe we want to double check the distance towards the, you see, shall we just, keep this one and remove this one? or remove them both. I don't know. We have a way to investigate, or maybe want to remove more stones. You see, this was one of the filters we had to, manipulate the stones that are on the very edge. And then we have all the other sliders that are working for us, like the size of the stone and the distance between the lines and the distance between the stones themselves, if you want them to be more spread apart. I think that we're pretty close to the ideal layout here.
I think so too.
Okay, so I think we're pretty much done with this. So maybe we want to bake all the diamonds that we will later use for rendering. So we want to go bake. It's a good idea to group them. And we can turn off the visualization for a grasshopper. Okay, so this is pretty nice, pretty decent. And it's something that the good thing, as we said, is that you can apply this definition to different shapes and the logic will be the same. And maybe we'll show you the output of the other ring that we had during our brief. So remember, this is going to be pretty much this one. We still have to make this second variation. And then we will end up with a couple of renderings just to show the customer the final work.
All right, so what's left now is just to render this project so we can show to the customer. Let's hope that they like it. And then what's next? Well, what's the next project?
Oh, we have a nice new rhino jewelry story waiting for us. And the brief is quite interesting. It's a collection of pieces based on granulation. That's an ancient Etruscan technology. And it's going to be fun, mixing that to contemporary tools like Rhino and Grasshopper and see what we can finally produce.
I can't wait to work on it.